Oh, on the right-hand side, there's that picture again of Gene Cernan taking a double drive tube. And thanks to Ben Feist for Apollo 17 in real time. If you haven't looked at this, you have to watch as much of the surface activity as you can, especially if you think about Artemis and what it's like to be on the surface as an astronaut. Really, really interesting stuff. So this is done as part of the Apollo Next Generation Sample Analysis Program. Thank you very much, Chip Shearer, for leading this, and we were part of the consortium that Chip led, looking at the core. And so we're addressing this question of the light mantle deposit because that's where the core was taken. You can see the red asterisk there. The red star. And then on the right-hand side, this is an XCT image. This is one of the really great, as you heard in the previous talk, it's one of the really great next-generation tools that we have to be able to look. You can see very clearly here, the contrast is set so that you can see the clasts in the core. This is 73002, the upper part of the double drive tube, but we have a similar image to this, or it's a whole suite of images for 73001, the lower part of the core. Okay, so questions. There's this beautiful light mantle at the base of the South Massif at the Apollo 17 site, and this was one of the science objectives of the mission, was to try to determine what the origin of this was, and in particular, there's a ray of Tycho that crosses the site, and the idea is that perhaps secondaries from Tycho struck the top of South Massif. You can actually see the secondary craters, the crater clusters, and there's a crater cluster in the Central Valley floor, thinking that if this is from Tycho and one could determine the exposure of the rocks in this event, that you could date Tycho. And indeed, that was done. We'll come to that. So the question has come up in recent years, looking at L-rock images such as this one, that perhaps, and let's see if the laser, yes, it's going to work, that perhaps there are two deposits. You see that there's a brighter, higher albedo deposit here, and then a lower albedo portion of that, the so-called thumb here, and this became evident in the L-rock images. And so certain individuals, one astronaut, Harrison Schmitt, and others looking at this said maybe there were two deposits, or maybe there were multiple deposits. And so perhaps the Station 3 core double drive tube would penetrate this, or would give us some clarity on this. If there were two deposits that were thin and they were penetrated, we should see that in something like the maturity data. And so what does what does the composition of the core reveal about the light mantle deposit itself? So that's what we'll look at. Hypotheses, even prior to the Apollo 17 mission, secondaries from Tycho were observed, as I mentioned, and it's possible, and this is something that Beriba Lukita proposed, is that tertiary ejecta sprayed from those secondary impacts from the top of the Massif actually produced the deposit at the base of the Massif, either by overturning material and making it appear brighter, which is what happens with when you expose underlying material and lower its maturity, or perhaps seismic shaking from a jolt of the secondary impacts. Exposure ages were determined for rocks from the Central Valley, as well as some of the materials in the light mantle. And even though there was quite a range of ages, there was a pretty good cluster at about 110, 107 million years. And so that was attributed to Tycho. And by the way, Drozd et al. And others who worked on those exposure ages were working right here at Washington University at the time in the physics department. So recent reassessments, again, Jack Schmitt et al. Have looked at potential movement on the Lee-Lincoln Fault as a possible cause of seismic shaking. And this is perhaps benefited by looking at the crater distribution, crater frequency distribution along regolith on either side of the fault, and coming up with the idea that looks like there's probably been relatively recent motion on it. So we're going to look at this with the double drive tube, the composition, maturity, and stratigraphy. What do we see? This is largely work done by Mason Newman, one of our graduate students here, who has just finished his PhD in part working on this. He did a tremendous amount of chemistry, and we'll talk about that. But what you see here on the set of images, first, here's X-ray computed tomography, again showing the clasts. Here's reflectance. So spectral reflectance was done by Sun and Lucy, a very nice study, and that was published, the upper part. And then, so we have vis near IR spectroscopy of the core, and then isobesivar FeO was determined by Dick Morris using his technique that's proven to be very valuable over the years. And you can see the data here. Initially, relatively mature, isobesivar FeO of 60, and then those values typically for less than 1 millimeter fines may go up to 80 or 90 for very mature surfaces, but 60 is still mature. And then with a decrease in about 10 centimeters, it goes down to 20 and then sets at 20, which is a very immature value, all the way to the bottom. So you notice that there are no spikes there. So we have, and then we have FeO and TiO2. Mason determined about 43 elements using ICP mass spectrometry. And we show FeO and TiO2 because you see FeO is a little higher at the top, and then it decreases through this upper 10 centimeters. TiO2 does the same thing, and when you see that, you say, that's a high titanium basalt component that's part of that, but certainly not pure. But that regolith has been contributed to by perhaps an impact. You can see the dark area up here in the reflectance. That is material that has more Mare basalt in it than lower in the core. So there's this upper disturbed zone, and then a relatively uniform lower zone, and it's immature. Now what you see, you look at the iron carefully, you see that it actually increases a little bit as you go down, and we'll explore what that means. Titanium, it's not so obvious, but it also increases slightly from this position here. There's a lot of interesting detail here about material lost on the surface of the moon when this double drive tube was taken apart and then the individual parts were capped. Lessons for future drive tube collection.
3 minutes.
But that's another talk. Okay, thanks. So Mason conducted a mixing model here using components that were determined some years ago by Korotev and Kremser, components from across the Apollo 17 site, and here we just focus on a few of these, but these are the key components at this site: high titanium Mare basalt, noritic impact breccia, a northocytic norite, meteoritic input, which is very low but not trivial, not zero, and then volcanic glass. And I've just taken the liberty to put some arrows on here to kind of guide your eyes to trends. Okay, so what we see is that there's if we look at the lower part of this core, there's a very slightly increasing high titanium basalt trend, noritic impact melt breccias increase, anorthositic norite decreases, meteoritic component, except for a few spikes, pretty much stays constant, and then orange glass again increases toward the bottom. Okay, so what could be causing this? One thing about these components, noritic impact melt breccia, that's the very common impact melt that's found at the Apollo 17 site. A couple of varieties, poikilotic and aphanitic, but those, it's an average composition. And then the anorthositic norite is more of a feldspathic sort of old upper crustal composition. Okay, so we see these trends, and we have to try to explain those. And so we have some conclusions here, or inferences, if you will. It's really tough to try to say exactly how this landslide formed, but the best we can do to explain the stratigraphy that we see is with a relatively, in the lower part, we'll look at the lower part here, the lower zone, a relatively quiescent landslide that's thin. When you look at the slope of South Massif, you really don't see a prominent landslide scar.
1 minute.
Thanks. You almost can't tell that there was a material stripped from there, at least looking at the topography. So we think it was thin. And it rides out over the valley floor and sort of inverts the stratigraphy of what we see on the South Massif slopes. So we have, that's how we get a little bit higher, a little higher Mare basalt component at the bottom of this and a little bit lower at the top. So we don't see evidence for two landslides. We don't see a break in the maturity that you might expect if there was an older
20
landslide and a younger
seconds.
one. Okay, thanks. We're getting there. So this is our interpretive model. Okay, thank you.